Well, thank you for coming. I would like to introduce Thomas Goldstein. We're very happy to have him here. Has his PhD from the University of California, Los Angeles, and he's coming here he has a postdoctoral research position at Rice University with Rich Baraniak, very well-known. He also has done a postdoc at Stanford. He did his PhD with been working with some of the leaders in our area, in the areas that Thomas is in especially. His research interests in optimization and its application to imaging and biomedical applications. And just one thing about Thomas's research practices, the split Bregman method for L1 regularization problems that was published in 2009 and has already been cited 600 times. So something for all of our PhD students to get on there as well, right? So Thomas, I'll let you go ahead and give your talk.
Thank you. All right, so today we're going to talk about single pixel video cameras. And the work I'm going to be presenting is a collaborative effort between Rice University and also between InView Corporation. InView is our industrial collaborator. And they're currently taking the theory we developed at Rice and they're building hardware implementations for cameras, and they're working closely with Lockheed Martin. So a little bit about single pixel video. What does it mean to be a single pixel camera? A conventional camera uses a very large detector array where you have one detector per pixel. So it's usually either based on a CMOS or CCD photodetector array. You actually sense on a pixel basis, meaning you have one single sensor per pixel. And there's essentially no reconstruction pipeline. The data is acquired in the image domain. A single pixel camera, on the other hand, only has one single detector. We have one single detector for the entire image, and every measurement that is acquired is going to be global in the sense that it encodes information about the entire and the way that we accomplish this is using what's called a coded aperture, which in some sense muddles information from different parts of the image and allows us to acquire this global information with a single detector. So before we go into the details of how this works, the question is, why would you want to build a single pixel camera? We live in a world with a lot of pixels. You can buy a 10 megapixel CCD array for about $3. So why would you want to go to an architecture that only has one single detector? And the answer is, there are image modalities where detectors are very expensive. And one of the image modalities that we're targeting is SWIR, which is shortwave infrared imaging. And shortwave infrared imaging is very expensive. Most of the detection uses indium gallium arsenide detectors, which are orders of magnitude more expensive than conventional CCD arrays. And SWIR imaging is useful in a variety of applications. So the military is interested in SWIR because of what's called the night sky radiance phenomenon. So during the day, the sun, in essence, charges up the stratosphere, and then at night, it radiates SWIR. So actually at night, even when it's very dark, the Earth is actually very bright in the SWIR domain. And so for night vision, it's very productive to work in the SWIR domain. It's something that the military is interested in. SWIR is also useful because it can see through fog and smoke. Because the wavelength of electromagnetic radiation we're using is longer, it doesn't get interfered with by small particles in the air. So here's an example of that. This is a forest fire image. It's in the same location, image with two different cameras. In the visible domain, you'll see that the image is highly occluded by smoke. But in the SWIR domain, you can see through the smoke almost perfectly. So firefighters are interested in this. The Navy is interested in it because it can see through sea fog. People are also interested in SWIR in the semiconductor industry because SWIR can see through thin layers of silicon wafers. And as a result, it can see types of manufacturing defects that conventional imaging can't. So this is actually a really big industry. So in science and military, people use a lot of SWIR imaging. Here's just a list of various applications. Like I mentioned, firefighting is a big application. Weapons sight for night vision is a big application. But this is a fairly large industry, and InView is trying to address a number of applications in this industry by producing a variety of different products. And the advantage of the single pixel architecture is that because we can get down to one detector, we don't need large arrays of these indium gallium arsenide detectors. We can manufacture cameras that are much less expensive than conventional cameras that are already available in the market. And InView's product line is looking to be about an order of magnitude cheaper than anything else that's currently available on the market. So how do these single pixel cameras work? Rather than using a CCD array that has an array of photodetectors, we use what's called a DMD, a digital micromirror device. And what it is it's an array of tiny mirrors. And each of those mirrors sits on a small pivoting head. And by changing the position of the mirrors, we can either cant the mirror so that light gets directed toward the single detector, or light gets directed away from the single detector. So here's a schematic view of how a single pixel camera works. We have some image we would like to acquire. We focus the light from that image onto the DMD, and we load some sort of pattern onto the DMD, where each mirror is either facing toward or away from the detector. And then we acquire a single measurement. And we do this for a variety of different DMD patterns. And each of these measurements encodes information about a variety of different pixels from the image. So here's some pictures of actual implementations of these cameras. So this is the first prototype camera that we built at InView. And it's built from a broken Sony point-and-shoot camera and a Cheerios box. Here's a slightly more high-tech implementation, and this is on Kevin Kelly's optical table at Rice University. And then this is the InView 210. So this is the prototype for InView's first product. It's supposed to ship within the next 3 months. And it fits into a box that's about 6 inches cubed. So this is the closest we have to commercial implementation right now. And the question is, what advantages does sensing with the DMD give you? How do these imaging protocols work? So every time we take a measurement, we load a DMD pattern onto the device. And what we acquire is, in a sense, an average of certain pixels within the image. So every pixel in the image corresponds to an individual mirror on the DMD. If the mirror is pointed toward the detector, we say that we acquire that pixel with coefficient 1. And if it's canted away from the detector, we have a pixel with coefficient -1. So what the DMD is essentially acquiring is inner products of the unknown image X with these measurement vectors phi, where phi is a binary vector of +1s and -1s. And we accumulate a number of measurements, and if we dump these vectors phi into the rows of a matrix, we can write our measurement matrix as capital Phi. And what we've essentially acquired is a system of equations where phi times our unknown vector x produces these coded measurements b. And we want to solve some sort of inverse problem to recover x. So the question is, why would you not just sense on a pixel basis? You could, for example, divert all the light from all of the pixels except for one away from the detector, and you measure that one individual pixel, and then you could measure the next pixel. So why not just measure on a pixel basis? And the answer is that single pixel cameras exploit compressive sensing, and this allows us to reconstruct the images using far fewer measurements than you would need if you were to reconstruct in a pixel by pixel basis. So here's a little crash course in compressive sensing and how it works. Compressive sensing is based on the fact that images are not really random. If you look at random arrays of numbers, it looks like static that you would see if you turn on the TV and you're not tuned into any particular channel. And you could generate millions upon millions of these random arrays, and it would never look like an image that had any structure. And what this tells you is that, in some sense, the set of images is a very small subset of Rn. So the set of images is a very small subset inside of this set of potential random images. If we could mathematically characterize that subset, that would give us a lot of information that we could use for our reconstructions. The question is, how do we actually do this mathematical characterization? The characterization that we use in compressive sensing is based on the fact that images are compressible. And as a simple demonstration of this fact, I've taken a test image. This is just a simple MRI brain image. I took the wavelet transform, and I threw away 85% of the information. I just threw out 85% of the coefficients, and I reconstructed it using the largest 15% of the coefficients. And you can see that visually, the two reconstructions are almost indistinguishable. And the reason why is, if you look at the wavelet transform, you'll see that, so this is the histogram of the wavelet transform. Almost all of the wavelet coefficients are piled up near 0. Almost all of the wavelet coefficients have very small magnitude. And as a result, they contribute almost nothing to the energy in the final reconstructed image. The only wavelet coefficients you need to do a reconstruction are these large wavelet coefficients that lie out here, and there's very few of those. So what that tells you is, in principle, it should be possible to reconstruct an image using very few measurements. The problem is that we don't have any adaptive way to actually sense these wavelet coefficients directly. We don't know which wavelet coefficients are significant, and we have no way of directly measuring wavelet coefficients. But it turns out that we can recover those wavelet coefficients directly using compressive sensing. So the idea behind compressive sensing is you have some sparse vector. This could, for example, be a wavelet representation of our image. Most of the coefficients are 0, and some of them are non-zeros. The non-zeros here represent the largest weighted wavelet coefficients. You acquire measurements by multiplying the image by some matrix phi. So in our case, this would be like our +1, -1 matrices that we use on a single pixel camera. And you acquire a small number of measurements y. And it turns out that, provided that this vector you're trying to measure is sparse, you can actually reconstruct it exactly using a very small number of measurements, provided that this sensing matrix phi is constructed properly. So here's an example of an exact recovery theorem. It says, how do we have to design the matrix phi in order to guarantee this sort of exact recovery? And for those of you that are familiar with compressive sensing, the most famous exact recovery theorem is called the restricted isometry property. And this is a little bit different than the more conventional theorem, but it's more applicable to single pixel cameras. So the question is, what properties of phi will guarantee exact recovery? The easiest construction of phi is you subsample the rows of an orthogonal transform. So you take some orthogonal transform matrix, you randomly subsample a set of rows from it, and that generates the matrix phi. But this only works if your orthogonal matrix is structured properly. And so we define what's called the incoherence of phi, which just measures the maximal element in the matrix phi. And in a sense, this just measures how evenly we've spread energy over the matrix phi. If you look, for example, at an identity matrix has all the energy piled up along the diagonal. If you spread that energy out more evenly, then you can get smaller entries in the matrix. So in some sense, the incoherence is just measuring how evenly you spread the energy over the orthogonal matrix. Here's what the exact reconstruction theorem says. It says, suppose that your measurement operator is formed by subsampling rows from an orthogonal matrix. Then we can get exact recovery with high probability, provided that we take a number of measurements that's proportional to some bound that involves the incoherence of the matrix, and it involves the logarithm of the number of pixels in the image. So if we want to acquire an n pixel image using compressive sensing, we actually only need log of n measurements rather than taking n measurements. And so as n gets large, asymptotically, you really win by using these compressive reconstructions where you can take far fewer measurements than you would need to using a conventional reconstruction method. So one way that we can build an orthogonal matrix for our application is using a HADAMARD matrix. So we need to build matrices that have only +1 and -1 coefficients because that's what we can load onto the DMD. And HADAMARD has a simple construction. It starts with a 2x2 orthogonal matrix, just has 3 1s and a single -1. And then we build larger and larger transforms by tiling the smaller transforms and applying the same plus or minus 1 coefficients to those matrices. So we do a simple tiling of 2x2 matrices, and we get H4, which is the 4x4 Hadamard transform. And then we can bootstrap this up to larger and larger matrices by taking the Kronecker product of a smaller matrix with this matrix H2. So this is what a simple image acquisition protocol looks like. You encode rows of the Hadamard matrix onto the DMD, which gives you a sequence of plus or minus 1s. You get an inner product with the image. We acquire a Hadamard mode of the image. Then we accumulate multiple Hadamard modes, and that's where this measurement operator phi comes from. So in our case, our measurement operator is going to look like R times H, where H is a Hadamard transform, and then R is a matrix. It's a diagonal matrix that just rips out the rows of the Hadamard transform that we've measured. So what we're saying is, when you take X, you hit it with the Hadamard transform, and then you rip out the rows that we've measured, the result has to be compatible with the measurements B that we took from the device. And then the recovery consists of finding a sparse solution to this system of equations. So you have to find some solution to the system where X is sparse. And I'm just going to mention a few things about image recovery right now, and we're going to talk more about this later. But we're trying to find a sparse solution, to this system. And we need to have some sort of sparsity model for our image. We need to enforce that it's sparse in some domain. One approach is to use a wavelet transform, but we found that it actually works much better to assume that it has a sparse gradient. And so what we want to enforce is that the image has small total variation. So total variation just measures the L1 norm of the gradient. And if you solve an optimization problem involving the L1 norm of the gradient, you get back something that has a sparse representation under the gradient transform. So the types of variational reconstructions we use, we solve problems with objective functions that look like this. We want to minimize the energy with two terms. The first term says that the Hadamard modes of our image X have to look like data that we've acquired. The second term says that the image has to be smooth in a total variation sense. So here's some examples of actual reconstructions. So this is from the InView 210, which is the prototype that I showed earlier. And these images are undersampled by a factor of 10 to 1. So we've only taken one measurement for every 10 pixels in the image. And you can see that you can actually get back fairly good image quality. Here's a detailed view of the image. We can actually get back pretty fine-scale details using a relatively small number of measurements, much smaller than you would if you were to sense in the pixel domain. So the question now is, how can we push this forward to doing video instead of still imaging? And video presents a lot of challenges that still imaging does not. So with still imaging, we have lots of data available. There's lots of data available with still images because we can take them over a long period of time. The longer we have to acquire data, the more data we can acquire because we can load more patterns onto the DMD. They have relatively low memory requirements. Storing an image in memory is much easier than storing a video in memory, so low memory requirements. And we can do processing offline. It's generally not expected that your image comes back completely instantaneously. If there's a period of time before the image comes back, that's usually fine for still imaging purposes. Video, on the other hand, is much more difficult. Because objects are moving, we have a much shorter time acquisition window. The moving objects produce aliasing artifacts. So we're acquiring data over time, but the objects move and produce, in some sense, smearing of the object as we acquire data. And the object motion can get aliased into the Hadamard transform in a bad way, and that creates aliasing artifacts. There's limited data because we have to be acquiring at a speed that's fast. We have to acquire data quickly relative to the speed that the objects are moving. High memory requirements because you have to fit a video on the reconstruction device. And for that reason, fast numerical methods are really essential if you want to make this sort of reconstruction happen in real time. So here's some requirements that we would like our video reconstruction to have. First of all, we would like to have two reconstruction modes. We would like to have a conventional reconstruction mode that does non-compressive reconstructions. And the reason why we would like this is for a number of reasons. First of all, focusing the camera in the compressive domain is difficult. If you can do conventional reconstructions using a data set, it's much easier to use conventional focusing techniques. The size, weight, and power requirements of conventional reconstructions are lower than compressive reconstructions. We can use the non-compressive reconstructions to do motion compensation. So we can use these low-resolution, non-compressive previews to predict the motion within the image and use that to enhance the compressive reconstructions. And finally, one requirement we would like for these methods is we'd like to be able to use the same data set from the DMD to reconstruct previews at any resolution. And on top of that, we want to be able to do a compressive reconstruction at the highest possible resolution. So for the full resolution compressive reconstruction, we would like it to be highly compressive. The reason why is because high compression ratio means high temporal resolution. If we can reconstruct a frame using a very small number of measurements, that means that the time window it took to acquire those measurements is short. And as a result, we get much better temporal resolution. We want the reconstruction to happen on the device in real time. And for that reason, the numerical methods we can use are very constrained. We can only use numerical methods that rely on very efficient transforms. We can't do things that, say, require us to solve large systems of equations. That just won't happen in real time on the device. So the first thing we would like to have is these low-resolution previews. So just to mention a few things about the theory behind these low-resolution previews, let's say that our full-resolution image has n pixels. The data we acquire looks like this. Phi times x sub n is equal to b. This is the data that we've acquired. We would like to be able to acquire a low-resolution image, x sub little n, that has far fewer pixels. But we need to have a way of measuring how well the low resolution image matches the data that we've acquired, which is on a higher resolution scale. So the way we do this is we define an interpolation or prolongation operator P, and we hit the low resolution image with this interpolation operator to bring it up to the high resolution, and then we can hit it with our measurement matrix phi and measure how well, how compatible it is with the measurements that we've obtained. But there's some requirements that we need to apply to both the interpolation operator and the measurement matrix phi in order to make this effective. First of all, phi has to be appropriate for compressive sensing. So phi has to be a subsampled orthogonal transform. Phi has to have a fast transform available. If it doesn't have, say, an n log n transform, like the HADAMARD transform does, it won't be computationally tractable to use it on the device. It can only have plus or minus 1 entries because it has to be loadable onto the DMD. And finally, the toughest requirement of all is that the product of phi and p also has to be an orthogonal fast transform. Reason being that this is the equation that we solve to obtain the low resolution preview. If phi times p has a bad structure, it'll be too expensive to solve this problem. We want the product of phi and p to still be an orthogonal transform so that we can just apply its adjoint in order to reconstruct the image. So there's a few things that go into the construction of these sensing operators phi. The first thing we need is we need a vectorization that will map a two-dimensional image into a single vector. The reason why is because the transforms are going to act on vectors. The Hadamard transform acts on vectors. And so we need a way of converting the image into a vector so that we can hit it with a transform. The most obvious way to vectorize the image is just to do a row-by-row ordering. But it turns out that if you want to have low-resolution previews available, we need to do something a little bit more clever than that. And we use what's called the nested dissection embedding. Nested dissection is a concept from numerical linear algebra that's used to solve linear systems. But we're using it for a different purpose here. And the way it works is you take a block of pixels in the image. So this is an image with 64 pixels. You divide the set of pixels up into 4 subblocks, so 1 through 16, all the way through a subblock of 49 through 64. And you tile those subblocks in a clockwise way around the image. And then we recursively break each of those blocks up. So the 1 through 16 block is broken itself into 4 blocks, and those subblocks are tiled around the image in a clockwise fashion. And then this recursive decomposition keeps going down until you get to the pixel by pixel level. And what you end up with is you end up with an embedding of the image into a vector that has the property that every subblock of the image is mapped contiguously into the vector. So this 4 by 4 block here has coefficients 1 through 4. Or this 2 by 2 block has coefficients 1 through 4. If you go to a block of 4 by 4, you get coefficients 1 all the way through 16. So every subblock of the image is mapped contiguously into the vector that we're going to apply transforms to. The next ingredient we need is we need an effective transform that we can apply to that vector. And rather than apply the Hadamard transform does not allow you to construct these low resolution previews. We're going to find a new transform that we call the sum-to-1 transform. The sum-to-1 transform is built much like the Hadamard transform is, but it has a different stencil. So in this case, it's all plus 1s except for minus 1s that occur along the diagonal. And we can use this stencil to build larger and larger matrices by taking Kronecker products of the smaller matrices with the stencil, just like we did for the Hadamard transform. And it turns out that this defines a family of orthogonal transforms, and it has the property that every row of the transform sums to 1, as opposed to the Hadamard transform where every row sums to 0. And in addition to that, if you take a transform and you break it up into subblocks, it consists of a bunch of smaller subtransforms that each sum to 1. It turns out that this sum-to-1 property is going to be important when we construct low-resolution previews. So how do these low-resolution previews work? Suppose that we have some row from our measurement operator phi. In this case, it's just a row from the sum-to-1 transform, and it consists of a whole bunch of plus 1s and minus 1s. So this is an example of a row of the sum-to-1 transform embedded into a two-dimensional array. So to generate a low-resolution preview, we have to solve the low-resolution preview equation where we've right multiplied our matrix by this interpolation operator P. So the interpolation operator works by taking blocks of pixels and mapping them down to, it takes a block of pixels and it maps it up to a patch in the image. So if you want to interpolate from a small image to a large image, you take each pixel in a small image and you just replicate it to create a tiling of patches that will go into the larger image. When you right multiply by the matrix P, it has the opposite effect. What it does is it takes blocks of the image and it sums them down to individual pixels. So what happens is when you right multiply by this matrix P, we take this sum-to-1 mode, we break it into blocks, and then the P operator sums all of these blocks together and replaces them with a single value. And because of the sum-to-1 property, it turns out that the sum over each of these blocks is going to give us back either a +1 or a -1. It turns out that if you cook up this row selection operator properly, it has the property that the plus or minus 1 pattern you get after you do this restriction corresponds to a mode from a lower resolution sum-to-1 transform. So we can prove some results about these low resolution previews. So the idea is that you, by right multiplying by the matrix P, we can take our high resolution modes and we can convert them to low resolution modes, which we can then use to reconstruct our low resolution image. And we can do a statistical analysis of the quality of the images that we reconstruct. And here's what we can prove. Suppose that you take the high resolution transform, S sub n, and we want to go down to little n pixels. What we do is we take the high resolution transform and we break the rows of the transform up into n groups. And we have the requirement that this row selection operator has to sample at least one row out of each of those n groups. Provided that you satisfy this property, then we can reconstruct our low resolution preview by rebinning the high resolution modes into modes of the low resolution transform, and then just applying the inverse transform in the low resolution space to get back our low resolution preview. And we can prove that this low resolution preview is optimal in the least squares sense. We can also prove some statistical results about the accuracy of these reconstructions. So there's a certain amount of randomness that goes into the reconstructions. And the reason why is because the matrix R is randomly subsampling rows from the sum-to-1 transform S. And so we can prove the following. Suppose that we look at the set of samplings that sample at least one row from each of those n groups. So they satisfy the properties that we need to construct those low resolution previews. If you uniformly sample R's from the set of matrices that satisfy this requirement, then we have that the expected value of each pixel in the low resolution preview is equal to the mean of the patch of pixels that it's supposed to represent in the high resolution preview, and that the variance of each pixel is equal to the mean of the variances of all of the patches in the image. So what this tells you is that the pixel you recover in the low resolution preview is an unbiased estimator of the mean of the patch that it should represent, and the accuracy is no worse than you would get if you were to randomly choose a representative pixel out of each patch. So here's an example of how this works. So here's a full resolution image. This was taken from the Rice University campus. We apply the sum-to-1 transform to move the image into the transform domain. So we end up with an array of transform coefficients. We then randomly sample those transform coefficients, and then we rebin them down into a transform space at a smaller resolution. So in this case, we've done a 64x restriction. And then you apply the inverse transform in that lower resolution space, and you get back a low resolution preview. So here's a comparison between the two. So we've downsampled by a factor of 64. You can see that the low resolution preview looks a lot like the original image, but it's a little bit more pixelated and blocky because we've restricted down to such a low resolution. So the next question is, how are we going to do the compressive reconstructions to get back to full resolution using the same data? So one ingredient that we need is we need some sort of sparsity transform. We need a sparsity model for videos. The easiest way to do video reconstruction is just to do a single frame-by-frame reconstruction. But if we look at this, the theory of our exact reconstructions, it tells us that that's not the best way to go. The theory says that if you have an n pixel image, you can reconstruct using only log of n pixels. Well, if each frame has n pixels, each frame is reconstructed using log of n pixels. If you did a frame-by-frame reconstruction, you would need log of n pixels for each frame. So the number of pixels you need is f times the log of n. But if you treat the entire problem like one large reconstruction, then all of the pixels come from the same image block. And our reconstruction theorem tells us that the number of measurements we need to take is proportional to the logarithm of n times f. So there's a massive complexity reduction you get from applying a sparsity transform in the time domain and treating everything like one large reconstruction as opposed to just going frame by frame. So the transform that we're going to apply in the time domain is very simple. We're using what we call a sparse-in-time model. And it's very similar to the total variation priors that we use in image processing. So total variation-based image processing assumes that images are piecewise constant in space. The sparse-in-time model, we're just going to add this assumption that we're also piecewise constant in time. And it seems like this is a pretty obvious generalization of a sparsely transform, but it turns out that mathematically, your time transform has to satisfy certain conditions to be compatible with your space transform. The sparsifying transform you use in the space domain has to generate sequences of frames that are also sparse in the time domain. And it turns out that total variation in time is compatible with total variation in space. The reason why is because if you assume that you're sparse in time, as we'll see, or if you assume that you're sparse in space, you also have to be sparse in time. But this is just an example of frames from a video that demonstrate why some types of videos would be sparse in time. If you look at, for example, surveillance videos where most of the background of the image isn't moving, you would expect these background pixels to be perfectly sparse in time. They have no changes in the time domain whatsoever. It's only the moving objects that generate changes in the time domain. But to demonstrate that sparse in time is compatible with sparse in space, we're going to use this simple test image. This is an image that was acquired by some of our collaborators at Merle Laboratories. This is from a high-speed camera that acquires images at 200 frames per second. And what we're going to do is we're just going to slice the image right down the middle, and we're going to look at the pixels that appear in this y direction over time. And here's what we get. So you can see that the image actually looks fairly sparse in the time dimension. Background pixels that aren't moving are perfectly sparse in time. There's no changes in time whatsoever. But also moving objects in the time domain look a lot like they did in the space domain. So if you were to assume that they're sparse under some sort of spatial transform, it's the same as assuming that they're sparse under time. So once we have our transforms in place and our sparsity model in place, the question is, how do we actually do these reconstructions? So what we do is we take our data stream coming off the DMD. So the DMD doesn't acquire one frame at a time. It loads vectors onto the DMD and then acquires data continuously through time. So what we do is we block groups of measurements together into frames. And then we do a reconstruction that looks a lot like it did for images. So we take each frame and we bin them all together into a long vector x. So x is just vertically accumulated from all the different frames you want to reconstruct simultaneously. And then our new row selector, just a block diagonal matrix that contains the row selectors for each frame. And then S is now a matrix, is a block diagonal matrix of the sum to one transforms. And what we get back is a reconstruction problem that looks just like it did for the two-dimensional case, except that now these vectors represent multi-frame quantities. So now instead of a two-dimensional total variation, we have a three-dimensional total variation that acts in space and time. And then we have a compatibility condition that says that the measurements we acquire the vector we require, the image we reconstruct has to be compatible with the data that we've acquired. So the question at this point is, how do we actually solve this problem numerically? We would like to be able to get real-time video off the device. And that means that we're going to have to use very efficient numerical methods in order to solve these problems. So the ideal methods we would like to use are splitting methods that have very simple substeps. And we need to exploit the problem structure. We have a lot of structure to exploit here. Total variation is a very simple differencing operator to apply. And the sensing matrices we've used are subsampled from orthogonal matrices. That gives us a lot of mathematical structure that we can exploit to solve these problems. Also, the methods we develop have to be parallelizable. And they have to be very low memory. And the reason why is because these are going to be implemented on an embedded platform. We're targeting FPGA platforms that will actually be on the device. But the memory footprint that you can fit on an FPGA is much smaller than you could fit on a conventional computer. As a result, we need to have very low memory algorithms. And the solution we've chosen are what are called primal-dual hybrid gradient algorithms. These were proposed by a research group at UCLA in 2010, but there's a lot of very similar algorithms that appeared in the literature before that. And these algorithms are typically used for large-scale linear programming. But it turns out that for this particular problem, these algorithms are very effective. So here's how the PDHG methods work. So we begin by creating what's called a primal dual formulation of this problem. So we begin with a total variation regularized problem, but the total variation norm is not differentiable, and we want to eliminate that non-differentiability. So what we do is we exploit the following fact. You can write the absolute value of x as a maximization in the following way. You say it's the maximum of the product of x and p, where p is constrained to lie between -1 and 1. So if x is equal to +1, then this maximization will happen when p is equal to +1, and you just get back x. If x is equal to -1, the max occurs when p is -1, and you get back -x. So this maximization problem gives you back the absolute value of x. And we can generalize this to the L1 norm of the gradient by writing this as the dot product of the gradient of x with this vector p, where p has a similar constraint. In this case, the component-wise norm of p has to be less than or equal to 1. And so this is called the dual formulation of total variation. And this gives us a saddle point problem. So we took the original minimization problem and we replaced the total variation with a maximum over p, and that eliminates the non-differentiability of the problem. And finally, we're going to write this as an unconstrained problem. We're maximizing with respect to p to get back total variation here, and we're still minimizing with respect to x. But we've dropped these constraints on p, and instead we've written them here as an indicator function. So the indicator function of p, it's infinity when p does not satisfy these constraints, and it's 0 when these constraints are satisfied by p. So all we've done is we've just taken this constraint on p and we've written it out here as an indicator function. So here's how the primal dual hybrid gradient methods work. There's two steps. First, we look at the primal variable, which is x, and we want to minimize for x, and that proceeds in two steps. First, we look at the gradient term, and we proceed by doing a gradient descent step for x. So we compute the gradient with respect to x, and we just do a gradient descent starting with xk and marching down the gradient with some time step tau, and that gives us an approximation x hat. Next, we have to deal with this L2 penalty term here, and we deal with that using a backward step or a proximal step. So we have a step that says start with your x hat that you got from the gradient descent step, and then try to minimize the L2 energy subject to a penalty that says don't go too far away from the x hat you got on the previous step. So if any of you are familiar with forward-backward splitting, it looks a lot like you're doing forward-backward splitting on the primal variables. The next step is called the prediction step. So we take xk plus 1, and we just add to it the difference between xk plus 1 and xk. So we say, look how far you went between the current iterate and the last iterate, and just go that much further again. That gives you your prediction x hat. And then we use that to do a forward-backward splitting step on the dual variables. So we do something very similar to what we did on x, but now we're maximizing for p. So we start with pk, and then we add to it the gradient with respect to p to do a gradient ascent. And then finally, we do a proximal step where we do a minimization involving this indicator function. And this proximal step turns out to be a reprojection of p into this L1 ball constraint. And that's something that's easy to compute explicitly. So every step of this algorithm is simple and explicit, except for this L2 minimization step. We have to solve this quadratic minimization problem somehow. If we were to use a conventional iterative method to solve it, it would be too slow to do on the device. But it turns out that because of the structure of PDHG for this particular problem, we can solve this analytically. So we begin with the quadratic minimization problem we want to solve, and we write out the optimality condition, which just says that the gradient of this energy has to be equal to 0. And this has two terms. It has a term that just involves our variable x multiplied by a time step tau, and that came from this proximal term that says x can't get too far away from the previous approximation. And then we have a term that involves sum-to-1 transforms and row selector matrices, and that comes from this fidelity term in our energy. We can combine both of those terms together into one big system of equations. And then what we do is we just write the identity as the product of the sum-to-1 transform with its adjoint. And this works because the sum-to-1 transform is cooked up to be orthogonal. Once we do that, both terms in the energy involve a sum-to-1 transform. So we can factor those transforms out to the side. And what's left inside is just a diagonal matrix. And so we can use the orthogonality of the sum-to-1 transforms to move them to the other side of the system. And we can just divide out this diagonal operator. And what we get is an explicit solution for this L2 minimization problem that only requires us to solve two fast transforms. So here's the entire algorithm for solving this problem. It's very simple. It has a very small memory footprint. So we just do our gradient descent for x, and then you do your proximal step, which just requires two sum-to-1 transforms. You do your prediction step, and then you do a gradient ascent for p, and you just reproject that back into the L1 unit ball. It's a very simple iterative method, and they're provided that your time steps, tau and sigma, satisfy certain conditions, you're guaranteed that it converges. So here's some examples of different types of recoveries we can do in these videos. So this is a conventional recovery where we acquire the full transform domain before we do a reconstruction. In other words, we've acquired one measurement per pixel. So this is the amount of data we use to reconstruct a frame is equivalent to what you would get if you reconstructed in the pixel domain. And what you can see here is there's massive aliasing artifacts that occur on moving objects. And the reason why is because the object moves a lot during the data that's acquired for a particular frame. Also, because it takes so long to acquire the data, you can see that this reconstruction only runs at about 0.3 frames per second. So we get a relatively low temporal resolution if you try to actually acquire all of the transform data. So this is a low resolution preview. This is acquired at 7.8 frames per second because we need a lot less data in order to reconstruct it. And you'll see that now we no longer have aliasing artifacts, and we get much higher temporal resolution. But you can see that the image looks blocky. And the reason why is because we're acquiring it only a 64 by 64 resolution, whereas the original was 256 by 256. And then finally, here's the compressive reconstruction. And this is done using 30x acceleration. And you can see we get to 15 frames per second. So each frame requires half as much data as the original blocky reconstruction. So here's the low resolution preview. Using only half the data, we can get up to much higher resolution, and we can get twice the temporal resolution. So like I said, this is 30x accelerated over conventional reconstruction. And we get back high resolution because we're using this compressive sensing principle in order to get back to the resolution without using very many measurements. So here's an example of a detailed view. Here's a portion of the image that we're going to zoom in on. So here's a standard reconstruction, and you can see that you can't see any fine details. There's no fine resolution details because the aliasing artifacts destroy all of that information. So here's the low resolution preview, and now you can see that the boundary between the two trucks is more well defined. You can see the windshield on the red truck. So this is a lot better for moving objects than a standard reconstruction. And then finally, if you do the full resolution compressive reconstruction, you get back all of these fine resolution details. So the current work that we're doing is mostly hardware related. So the question is, how can you build a hardware implementation of these reconstruction algorithms? And like I said, we're targeting an FPGA platform. And these primal-dual hybrid gradient algorithms are very FPGA friendly, and that's one of the reasons why we chose them. The number of steps in the algorithm is very small. On an FPGA, you have a very limited number of gates to work with, and you actually have to build a hardware implementation of every step in the algorithm. If you have a very long, convoluted algorithm, then you very quickly run out of gates on the device. But by choosing something like FPGA that's parallelizable and has a very small footprint, you can fit a lot on these FPGAs. But there's some changes you have to make to the algorithms to make them hardware friendly. The first thing is we have to use what's called a fixed pipeline transform. So for the sum-to-one transform, instead of doing these recursive algorithms where we break the transform down into a set of smaller transforms, it's actually possible to build a fixed pipeline transform where you iterate over all of the data elements, and then you perform a permutation, and then you iterate again. And when you build an implementation that way, every stage of the transform is identical, as opposed to a recursive implementation where you have smaller and smaller transforms at each stage, and every stage of the transform is different. If you do that, then you can use the same gates on the device at every stage of the transform. It's much more FPGA friendly. And finally, we can only do fixed point arithmetic effectively on the FPGA. We can't do any floating point arithmetic. And as a result, you have to rescale the algorithms appropriately. You have to choose your time steps in a very clever way. But provided that you scale the problem appropriately, it's possible to make this work in fixed point arithmetic. We've built a real-time FPGA implementation that works for simple frame-by-frame reconstruction. And the problem we're working on now is building a new FPGA implementation that will actually do these compressive video reconstructions that can get up to higher resolutions. Some more future work we would like to do. We would like to be able to use this low-resolution preview to do motion compensation in order to enhance the effectiveness of the sparsity transforms that we're doing in time. If you can compensate for motion before you do the compressive reconstruction, you can do reconstructions that are even sparser in the time domain, and you can get up to even higher resolutions than we have now. We would also like to look into higher order sparsity transforms that work more effectively with smoother images than total variation does. Finally, some of our funding right now is to do hyperspectral imaging. So we'd actually like to build hyperspectral cameras that work in the compressive domain. And hyperspectral imaging is very expensive because the types of detectors that you need to work over a very wide range of wavelengths. But by using compression in the hyperspectral domain, it's possible to use much more simple detectors and still do hyperspectral imaging. And finally, we would like to do multi-scale numerics. We'd like to be able to use this low-resolution preview property to use the low-resolution reconstructions in order to enhance the speed of the high-resolution reconstructions, and that'll allow us to get up to even higher frame rates. So thank you very much. Questions?
So how fine of an image are you trying to represent after you've done all of your compression and everything else? Because I mean, it looks like that you can get a very accurate image, but at the same time, there's details that may make a difference in the full image. What they're looking for, I guess.
Right. So the compression, the idea behind compressive sensing is you can still get back really fine details, but the number of really fine details you can get back is limited. So the number of wavelet coefficients that you can recover is limited to some extent by the number of measurements that you take. So the number of wavelet coefficients you can recover is proportional to the number of measurements that you've taken. So it's not that you can't recover fine scale details, it's that you can only recover a certain amount of fine scale details. When you look at images that have very large oscillatory components, very fine scale textures, that's when you start to see blurring artifacts in these reconstructions. But actually, provided that most of your image is relatively smooth, you can still get back the same resolution that you would have originally. And you can actually see in some of these test images that the resolution you get back with the compressive reconstruction is very similar to the original resolution. But this is helpful to most of it back. Makes sense? Yeah.
L1 norms of linear operator.
Right. Right.
Can you work that out, or is that kind of a little bit of
It's not, the problem is the theory is not that TV is nonlinear, it's a gradient transform is linear, right? What? Right. So most of the theory that's out there applies to wavelet transforms, where you assume that you're L1 under some sort of wavelet transform. If you're using an orthogonal wavelet transform or a tight frame wavelet transform, then you can change the variables, right? And you get back to the same sort of L1 minimization problem that you see in conventional theory, and then all of these results apply. But it turns out that in practice, wavelets don't work as well as TV. And there are theoretical results that say that you can do compressive sensing with TV, but the bounds that you get, the bounds that you can get on the number of measurements are not as small as you have for, say, this result. This result is actually assuming that you're using an orthogonal wavelet operator. So the theory is weaker. The reason why is because TV is not invertible, and so you can't apply the same kind of theoretical analysis. The theoretical results are weaker, but in practice, it's pretty well accepted that TV gives you much more effective sparse representations. So in practice, the bound you end up with. And we actually have implementations. The first implementations we built were using wavelet theory, but the quality you can get is way better when you start using TV. But it's actually not backed up with these sort of theoretical. Sure. Yeah?
Usually when you solve problems, there is a coupling constant between the data term and the total variation. And it seems that in your problem you balance between them. You allow the constant is 1.
Well, that's a good point. Constants. So here's the constant, right? The constant here is mu. So we don't assume that the constant's 1. The question is, how do you choose this constant?
Exactly.
And on the FPGA, where we're doing a fixed point implementation, you don't have the luxury of adaptively choosing. You have to choose the constant, and you have to choose it in such a way that everything works out nice from the standpoint of integer arithmetic. But it turns out that choosing this constant is actually relatively easy. And the reason why is that if you choose a really small constant, total variation takes over and it really blurs out the features of your image. As you increase the constant, what happens is you start to get back features by you basically filling in elements of the vector x that account for large components of your measurements. And those correspond to image features, and you start to get those back. You eventually, as you increase mu, you start to get more and more of the signal back until you hit the point where there's nothing left but noise. And the noise corresponds to much smaller residuals than the image features do. And so what happens is if you plot the image error versus this parameter mu, what happens is you start increasing mu, and all point where the reconstruction almost doesn't change at all as you increase mu, until you increase mu above some threshold value where you start trying to fit the noise in the measurements back into the reconstruction X. It turns out that the threshold of that, where the noise starts to get aliased into the data, is much higher than the cutoff where the image features get recovered. So there's actually, there's an interval of about 2 orders of magnitude of wiggle room in the choice of the parameter mu. So what we actually do is we scale the data appropriately, and then we just choose a fixed constant mu that turns out to be very robust to the different types of data that we're trying to use. So I guess the answer to your question is choose a big mu. It's really hard to choose a mu that's too big. So you just choose a mu that's big enough to guarantee that you're going to get back almost all of the energy from the vector B. And it turns out that in practice that's actually pretty robust. Well, so we use the same mu for all videos. But like I said, that's assuming that you've scaled the magnitude of this vector B properly, so that there's to be some relation between the size of the value you choose for mu and the 2 norm of this vector B. And then we basically err on the side of choosing mu to be too large. And then that gives you an almost exact representation. You want to get back something where RS times X is almost exactly equal to B. And by erring on the side of choosing a huge mu, you actually get back something that's pretty effective. We don't have any data sets, and we chose one value of mu, and we don't have any test data sets where that hasn't been appropriate. We've tried things in various different light conditions and various types of textures, and it seems to be pretty robust. Yeah?
So like stripes, really
So yeah, there's a certain amount of jitter. Not too far than that. There's a certain amount of jitter that happens in the low resolution preview. The reason why is actually because we've only subsampled 4x4 blocks of the image. So what happens is if you look at those 4x4 blocks, they have 3 plus 1s and they have 1 minus 1 in the transform block. And every time you take a measurement, you change where the location of that minus 1 is. So if you have a vertical feature that passes through the image block, every other measurement is switching inside the transform that the minus 1 appears on. And that causes the image features to sort of shift back and forth a little bit. You don't have this problem when you go to higher resolutions. And actually the devices that we're working with have a resolution of about 1024 by 1024. And in that case, you're doing like downsampling. And once you do that, there's an almost random distribution of plus 1s and minus 1s inside your matrix. And so you don't see that same, you don't see that jitter when you do much more dramatic downsamplings. But with the test data that we have, because the original high-speed camera videos are at relatively low resolutions, we don't really have a luxury of doing that sort of downsampling. Yeah.
Since we're already on here, with the preview one, you don't do any compressive sensing of this.
There's no compression at all that goes into
so
this.
The point you wanted to make here is that you would always want to use the better mode compressive sensing.
Well, you wouldn't always want to use it. So the reason we do a low resolution preview is 2 reasons. First of all, in the future, we want to use this to do motion compensation to enhance the effectiveness of the high resolution compressive sensing. The other reason is running the FPGA to do the full resolution compressive sensing uses a ton of energy. And so it's nice to have a conventional reconstruction that has very low energy requirements that you can run all the time. And then you can either turn on the high resolution reconstruction, or you can actually you can look at the same data set later, and you can do almost like a CSI image enhancement type thing where you can actually use the exact same data set, and instead of doing a pixel by pixel reconstruction like this, you can actually go up to a higher resolution using a compressive reconstruction.
So even though compressive takes more energy, it's still faster, so you can get like.
No, it's not. Oh, I see what you're saying. The per frame reconstruction is not faster. The reconstruction of this is just a simple fast transform. So you've acquired, once you re-bin to these lower resolution transforms, you've actually acquired every transform coefficient at that low resolution. So you just apply the inverse transform to get the reconstruction. The reason that the frame rate is higher is because the amount of data, and believe it or not, the amount of data you need to get this is lower than the amount of data that you need to get the preview. You can actually use half as much data. And for that reason, the time it takes you to acquire each frame is lower. You get a higher frame rate. But the computation that goes into producing this is huge compared to it's about 200 times, about 200 fast transforms instead of a single low resolution fast transform.
Can you do this now in real time?
So we can do this at real time, but the power requirements are relatively high for a portable device. And so we can do it, but it's nice to have two different image acquisition methods so that you have this lower power acquisition where you're just taking one measurement per pixel, which is a more conventional acquisition, but then you have the option of going back and enhancing the resolution later, or even turning on the resolution in real time.